Hello, everyone. My name is Tuan. I'm from Singapore Management University, and today, on behalf of the co-authors, I would like to present our work, Bilateral Variational Autoencoder for Collaborative Filtering. This work is presented in Wisdom 2021. So, the problem that we are interested in this work is collaborative filtering. The objective is to learn from the set of user and item interactions in order to provide good recommendations to user. The problem of collaborative filtering is very important, and it uses a lot of applications ranging from the e-commerce website to social media and social networks. So the preference data is dyadic. Um, what does it mean by dyadic? So let's say we have the preference data, and most of the time, the preference data is being represented as an interaction matrix between user and item. In this case, I say the matrix R of size U by I. It is dyadic in its nature, meaning there are two ways to view the data matrix. First, we can view it by user, meaning view it by rows, and it actually consists of a collection of rows. The second way to view the rating matrix is by columns, which in this case we view by items, and is a set of collections of columns in this matrix. So one of the very successful model for collaborative filtering is variational autoencoder, or VAE for short. The model demonstrates a very competitive performance for collaborative filtering um, because the two ways nature in the preference data that we discussed earlier, it gives rise to two variants of the VAE. Uh, the first one I would like to introduce is the user VAE, where we view it row-wise, the rating matrix. Then the each of the row in the matrix gonna be input to the encoder. So the encoder gonna output the mean and the variance that characterize a distribution of user latent variable from which we can sample a representation, the U in this case. The representation is a compressed form of the input, and it can be used by a decoder to reconstruct the input. In the context of collaborative filtering, it will also try to reconstruct the missing values, which allow us to provide recommendations. Similarly, we can have the second variant, which is the item VAE, where now we take each input is a column in the interaction matrix that we saw earlier. So there are two drawbacks of VAE when applying to direct data. First, because the two variants, it cause ambiguity, which which one to use, the user VAE or the item VAE. And it also loses the inherent meaning of the data because it's dyadic in nature. Second, it is not straightforward how we can extend the VAE to accommodate the auxiliary information from both sides if available. So with that, we would like to introduce a new model to address the above concerns of a VAE architecture. So in this paper, we propose a model named Bilateral Variational Autoencoder, or BiVAE for short. We fix the asymmetry of the VAE architecture by learning the variational representation for both user and item simultaneously. The BiVAE model consists of user and item encoder, which characterize the distribution of user and item latent representation, from which we can sample theta u and beta I. Theta u is the user representation, and beta I is the item representation. Both vector will be combined by a function f. to output the value RUI, measuring the interaction between the pair of user and item. The function f can be as simple as dot product or can be a deep neural network if we want to model a complex function. So in this framework, the distribution of RUI could be one from the exponential family, which covers many possibilities. Let's say for example, Poisson distribution, Gaussian distribution, Bernoulli distribution, just to give a few examples. So with the design, by VAE respect the two-way nature of dyadic data. So we can argue that it is more suitable for collaborative filtering than VAE. Another strong point, both user and item are modeled equivalently and symmetrically. The BiVAE architecture can be easily to extend to accommodate the auxiliary data from both sides if available. And that is not straightforward for the case of VAE architecture. As a concrete example, we would like to introduce a version of BiVAE with the Poisson likelihood. So the generative model, as demonstrated under the graphical model there, the generative model by VAE, we have the user and item representation are drawn from the unique Gaussian distribution, and the interaction, the the RUI are drawn from Poisson likelihood Poisson distribution, which is suitable for modeling counter data. Sometimes our interaction matrix is the well-known difficulty of learning this sort of latent variable model is lying in the intractability of the posterior distribution. It's intractable to estimate the posterior. So based on the idea of variational inference and the mean field assumption, we propose to estimate the posterior Joy distribution by the variational distribution in the following factorized form as shown there. And to estimate each of the individual posteriors, we follow the same treatment as VAE of using amortized inference. So that complete the BiVAE model under the variational bias framework. So now we are ready to fit our model to the data. So in terms of optimization, learning the BiVAE model is we are maximizing the evidence law about objective function as shown there, which is nothing special. But there's a couple of things that we want to emphasize. The optimization in practice is performed using stochastic optimization with the half of the reparameterization trick to get rid of the sampling operation to take the gradient. And for this BiVAE model, there's a tricky part of the user and item we optimize both simultaneously, and we derive a block stochastic optimization procedure. More details we provide in the paper, so please check it out to get a better understanding of how we actually perform optimization for BiVAE model. For the experiments, we actually do experiments on 7 real-world dataset. The way we conduct the experiment is that for each of the dataset, we actually split the data by 80, 10, 10% for training, validation, and test set respectively. So the validation going to be used to tool the hyperparameters of the model, and then we report the results on test set. For the experiments, we compared our BiVAE model with several baselines. We actually compare with various collaborative filtering approach, including the traditional factorization one like hierarchical Poisson factorization, Gaussian Poisson factorization, and as well as the state-of-the-art methods using the deep neural networks like NeuroMF or even the multiple variants of the variational autoencoders with a different likelihood. We employ 2 evaluation metrics, recall at K and DCGIK. They are well-established metrics to measure the performance of top K recommendation. First, in comparison with the different collaborative filtering methods, we see that the BiVAE model consistently outperforms the comparative baselines. The improvements over the baselines are statistically significant, tested with two-tail pair t-test, and the similar trends are observed on the other dataset as well. So with the spay limit, we only show 2 here, but the same trends are observed with the other dataset. We also compare the BiVAE model with the VAE, which is a direct baseline in our case, and with a different choice of likelihood. Here we show the Bernoulli likelihood and the Poisson likelihood. And two observations, we see that the BiVAE is robust regardless regarding the likelihood choices. And also the BiVAE outperforms the VAE regardless the choice of the likelihood. And we also, this one, we also experiment with the multiple data set and the similar trends observed with other data set as well. Another contribution that we want to emphasize in this paper is the proposed, we propose the method called constrained adaptive priors. So what is that? In optimizing the evidence lower bound, which is the elbow for short. The KL terms in the elbow can be expressed in the following form. We rewrite the KL terms, and we actually notice that maximizing the elbow leads to minimizing the mutual information between user and their latent representation. It's the same for items. And that could potentially lead to posterior collapse problem. So we propose constrained adaptive prior, or CAP for short, that learns adaptive transformation from pre-compute hyperparameters of user and items to leverage the posterior collapse. So the hyperparameters of user and item can be pre-computed from their auxiliary information, design information. And in this case, we see that the latent space is pushed by the independent to be independent from user and item. And with CAP, this is the form of the CAP where we actually have the adaptive transformation, the T and the B there, the T matrix and the B matrix there. And this is the generative model. And with the CAP, we can leverage the posterior collapse problem. Some of the experiment, we show here a couple of data sets that we experiment with the CAP, and we compare with the standard Gaussian priors. The comparison show that the CAP actually can improve performance significantly as compared to the standard Gaussian priors. And the comparison with other choice of priors also we reported in the paper. We define the statistics, so-called the latent variable activity, the following formula. And this one can actually compare the level of how active the latent dimensions of the user and the item. The meaning is that the more active the latent representation, the more information that latent representation actually capture from user and item. And in this one, we actually see that the CAP, the latent space of the CAP, and has higher variance than the latent space of standard Gaussian, which demonstrate that the CAP actually capture more information. With conclusions, we want to says that the BiVAE model achieves competitive performance for collaborative filtering. BiVAE with CAP, constrained adaptive prior, can mitigate the posterior collapse problem. The BiVAE could be also applied to other type of dyadic data, like a document word matrix. So yeah, if we can view the data in the form of a matrix and it's two-way in nature, as is dyadic data, then the BiVAE model can be applied. And it's also can be applied to other tasks like collaborative core clustering problem, for example. We make the code for the experiment available in the link below. And for additional questions, just contact me with the following address. So we made the code available in a library called Quoc. So Quoc is actually a Python library for recommended system. And the focus of the library is on supporting multimodal data like item, text description, image, user social networks. It consists of a rich collection of implementations of recommendation algorithms. The technical paper is published in the Journal of Machine Learning Research, GMLR, last year. So please check it out on our GitHub page. Thank you.